The James Webb Space Telescope measured how fast the universe is expanding, and there is a severe problem. The results have confirmed the biggest crisis in cosmology, the Hubble tension. This means that the universe is expanding at a rate faster than what our best cosmological model predicts, and no one knows why. This is important because it highlights a fundamental flaw in our understanding of the expanding universe. Earlier, astronomers thought the observed discrepancy was due to our technological limitation that might be overcome with next-generation observatories, such as the James Webb Space Telescope. But Webb's results made the crisis in cosmology worse. It shows that there is something that we are missing out in our calculations or observations, giving rise to this tension. So what is the Hubble tension, and why has it become such a serious problem for astronomers? What did the James Webb Space Telescope see that confirmed the cosmological crisis? Finally, and most importantly, what new physics would be revealed in the resolution of the Hubble tension? To understand the biggest crisis in cosmology, we need to go back 100 years to the 1920s. Two astronomers, Harlow Shapley and Herbert Curtis, were engaged in a serious debate now known as the Great Debate. At its core, this debate was about the scale of the universe. The question was simple yet profound. Was our Milky Way galaxy the entire universe, or were there other galaxies beyond it, making the universe much bigger than we thought? This question sounds odd today, but at that time, astronomers believed that the entire universe comprised just one galaxy, the Milky Way. Of course, we had pictures of other galaxies, such as the Andromeda Galaxy, but for a long time, they were considered star systems lying within the Milky Way. For the same reason, they were called spiral nebulae instead of galaxies. So, the controversy focused on whether or not the spiral nebulae were located within the Milky Way galaxy. Shapley believed that the Milky Way was about 300,000 light-years wide, and all the star systems existed well within the outskirts of the Milky Way. In other words, the Milky Way was the entire universe. On the other hand, Curtis argued that the nebulae were independent galaxies like our own Milky Way, located far, far away. The debate took place on April 26, 1920. It was a clash of visions where the scale of the universe and the nature of the nebulae were open questions. Unfortunately, there was no significant outcome of the debate. Astronomers were still divided. The answer to the question came from the arguments of neither Shapley nor Curtis, but from the meticulous work of an American astronomer named Edwin Hubble. In the 1920s, using the most powerful telescope of his time at the Mount Wilson Observatory, Hubble made an extraordinary discovery. He observed Cepheid variable stars in the Andromeda Nebula, which was then considered part of the Milky Way. Particularly, he measured the distance between us and the Cepheid variable star V1 in the Andromeda Galaxy. The distance turned out to be about 1 million light-years, about 3 times greater than Shapley's estimate of the Milky Way size. This means Curtis was right about the spiral nebulae. They were large galaxies, just like our own. Although Hubble's estimate was less than the distance we know today, it showed that the universe is substantially larger than previously believed. However, this discovery opened Pandora's box. It was about to give birth to a number that would become the root of one of the biggest unsolved problems in cosmology. As Edwin Hubble peered deeper into the cosmos, he observed an intriguing pattern. He discovered that galaxies in deep space were moving away from us, and the farther they were, the faster they seemed to be receding. So if v is the velocity at which a galaxy is receding, and d is the distance to that galaxy, then v is directly proportional to d. This seemingly simple relation gave birth to the most controversial number in astronomy, the Hubble constant. This number is the key to understanding the recent discovery made by the James Webb Space Telescope. The physical meaning of the Hubble constant is simple. It tells us how fast a galaxy is receding from us for every megaparsec it is away. A megaparsec is a unit of distance equal to approximately 3.26 million light-years. Let me explain with a simple example. Imagine there are two galaxies. Galaxy A is 1 megaparsec away from us, and Galaxy B is 2 megaparsecs away. If the value of the Hubble constant is 70 kilometers per second per megaparsec, then Galaxy A would be receding from us at a speed of 70 kilometers per second. Galaxy B, being twice as far, would be receding at 140 kilometers per second. Since it's 2 megaparsecs away, we multiply 2 by 70 kilometers per second per megaparsec. This expansion is not due to galaxies physically moving through space, but rather to space stretching itself. So, in essence, the Hubble constant tells us how fast the universe is expanding. You must be wondering where the problem is. It's a simple linear equation. All we have to do is measure the distance to Galaxy D and its velocity of recession, v. Plugging in the values, we would have our Hubble constant. Well, if it were only that easy. Calculating how fast the galaxy is moving away is easy. All we need to do is determine its redshift and find the velocity using a simple equation. However, measuring the distance has always been a problem. How do we accurately measure the distance to a galaxy that's millions of light years away? Astronomers found a clever way. They used a special class of stars known as Cepheid variables. Cepheid variables are stars that pulsate in a very regular way. They brighten and dim in a predictable pattern. In the early 1900s, Henrietta Swan-Leavitt studied plenty of Cepheid variables in the Magellanic Clouds and discovered a crucial relationship between their periods and luminosities. The rate at which a Cepheid star pulsates is directly related to its true brightness or luminosity. Simply put, the longer the pulsation period, the brighter the star. If you want to calculate the distance to a galaxy, you need to follow 3 steps. The first is to observe the pulsation. Astronomers observe a Cepheid variable in a distant galaxy and carefully measure how long it takes for the star to go through one full cycle of brightening and dimming. Since the period is related to its brightness, we can use the period-luminosity relation to measure how bright the star actually is. This is known as the absolute magnitude. So, if the star took 30 days to go through a full cycle, its absolute magnitude, or true brightness, is minus 4.85. The second step involves comparing apparent and true brightness. The star's apparent brightness, or how bright it appears from Earth, can be measured with telescopes. Let's say it turns out to be 24. Here's a fun fact. The naked eye limit is 6, meaning the star in our example is about 16 million times fainter than what we can see with the naked eye. The third and final step is the brightness-distance relationship. Here's where a bit of cosmic magic comes in. There's a basic rule in astronomy that if you know how truly bright something is, and you can measure how bright it appears, you can calculate how far away it is using a simple equation in astrophysics known as the distance modulus equation. So first, we observe the pulsation period of the star. Then we use the period-luminosity relation to determine the star's absolute brightness. After that, using our telescopes, we measured how bright the star appears from Earth. Finally, using a simple equation, we determine how far the star lies from us, which turns out to be 5.9 megaparsecs. In this way, using a single star of a special class, we have found the distance to the galaxy in which it lies. In place of Cepheids, astronomers also use Type 1a supernovae to determine the distance to their host galaxies. While Cepheids are useful in determining distance on a few tens of megaparsecs, Type 1a supernovae are helpful on the scale of a few hundred megaparsecs. Sometimes astronomers combine the two methods to confirm the distance measurement. With advanced technology and measurements, astronomers have settled on a value of around 73.4 kilometers per second per megaparsec, using Cepheid variables. But how were they so sure about this number? Well, they were not. That's why they wanted to use cosmological models to verify the number. If the results matched, they would be right about the expanding universe. However, if the values didn't match, it would indicate a fundamental flaw in our understanding of the cosmos. This independent method involved the Big Bang relic, the cosmic microwave background, or the CMB. The CMB is the oldest light in the universe, a faint glow left over from the Big Bang, permeating the entire cosmos. It provides a snapshot of the universe just 380,000 years after the Big Bang, before stars and galaxies formed. Measurements from the CMB are not directly reliant on the cosmic distance ladder, the series of steps astronomers use to measure distances in the universe, offering a way to cross-check results obtained from Cepheids and supernovae. Astronomers use satellites like the WMAP and the Planck spacecraft to map the CMB's tiny temperature fluctuations across the sky. These fluctuations reflect the density variations in the early universe and are related to various cosmological parameters, including the rate of the universe's expansion. When astronomers calculated the Hubble constant using these two methods, they expected to find the same value. However, they encountered a surprising twist. The value of the Hubble constant from the CMB method turned out to be around 67 kilometers per second per megaparsec, less than what was determined by using Cepheids and supernovae. The discrepancy between these two values may seem small, but it is statistically significant and beyond the expected margins of error for such precise measurements. This discrepancy is what's referred to as the Hubble tension, the biggest crisis in cosmology. Essentially, it's a conflict between the universe's expansion rate, as observed directly in our local neighborhood, versus the expansion rate inferred from the conditions of the early universe. Astronomers still had hopes. They thought the observed discrepancy could be due to the limited resolution of the Hubble and other giant telescopes. They eagerly awaited the results from the James Webb Space Telescope, hoping the infrared observatory would resolve the crisis. However, the results only confirmed their worst fears. Cepheid variable stars are commonly found in densely packed stellar regions, which is to say, they are seen in crowds. However, the presence of other stellar objects within Cepheid's field of view complicates the measurement of its brightness, affecting the accuracy of distance estimations. A notable example is a specific red spot identified as a Cepheid variable in NGC 5584. In images taken by the Hubble Space Telescope's Wide Field Camera 3, this fuzzy object appears surrounded by numerous other celestial bodies. In contrast, with its superior infrared capabilities, images captured by the Webb telescope depict the same Cepheid variable with greater clarity and, importantly, as a distant entity separate from neighboring stars. Scientists have observed several Cepheid variables in two galaxies, NGC 4258 and NGC 5584. NGC 4258 is a relatively nearby galaxy whose distance is well established. Meanwhile, NGC 5584, which hosted the Type 1a supernova SN1A 2007 AF, is a distant galaxy containing Cepheid variable stars. More than 320 Cepheid variable stars from these galaxies were analyzed using the Hubble and the James Webb Space Telescope to evaluate and compare their capabilities. The first row indicates the position of each variable star in the galaxy, NGC 4258, with periods ranging from 18 to 41 days. In this figure from the research paper, the Hubble images are marked in black, whereas the Webb images are highlighted in magenta. The Hubble images appear crowded, while the Webb images, thanks to their higher resolution, are comparatively less so. The distinction is the primary reason the research paper on this study is aptly titled "Crowded No More." Similarly, image patches from both the telescopes found in NGC 5584 are displayed for all Cepheids with periods ranging from 39 to 43 days, indicative of brighter Cepheids. Using these observations, the period magnitude relation was established for both galaxies, as depicted in the two panels. The data points highlighted in red are derived from the Webb filter, whereas the gray dots represent observations from the Hubble Space Telescope filter. What does this reveal? This comparison shows that the red data points follow the same trend as the gray ones. However, there is a noticeable reduction in the standard deviation for both galaxies. A lower standard deviation indicates reduced error, a trend clearly observed in the Webb data points. To confirm the results, the same team observed larger samples of Cepheid variables and supernovae in a total of 6 galaxies. To their surprise, they got consistent results that confirmed the Hubble tension. Based on this, the team confidently ruled out the measurement error as the cause of Hubble tension. So, the observations made by the James Webb Space Telescope have validated the value of the Hubble constant, confirming the crisis in cosmology. This means that the Hubble tension isn't a result of technological limitations or measurement uncertainties. Rather, it exposes a gap in our fundamental understanding of the universe. Now that the James Webb Space Telescope has confirmed the Hubble tension, we do not know what exactly we are missing. We may be making a mistake in distance measurements, or there's something wrong with our understanding of the cosmic microwave background, leading to a discrepancy between the two values. It's even possible that both the values are flawed, and an unknown factor is at play. There are 3 reasons why resolving the Hubble tension is critical. The first is testing the standard model of cosmology. The Hubble tension could indicate a potential flaw in the lambda cold dark matter model, the current best model of cosmology. This model incorporates the cosmological constant and cold dark matter to explain the evolution and structure of the cosmos. If the Hubble tension arises from inaccuracies in this model, resolving it could lead to significant revisions. The second is understanding dark energy. Dark energy, the mysterious force driving the accelerated expansion of the universe, makes up 68% of the observable universe. The Hubble constant is directly related to the rate of this expansion, so discrepancies in its measurement could offer new insights into the nature of dark energy. Finally, understanding the rate of cosmic expansion is key to predicting the universe's fate. Different expansion rates could imply different scenarios, from an endless expansion in which galaxies become increasingly isolated, to a big crunch in which the universe eventually collapses back in on itself, or even a big rip in which the fabric of space-time is torn apart. Resolving the Hubble tension is a step toward understanding our cosmic destiny. For that, astronomers are exploring different independent approaches to measure the universe's expansion rate. One method involves studying gravitational sources, such as merging black holes or compact objects accompanied by some optical light waves. Another approach involves measuring the distance to red giant stars by observing their helium flash, which offers a precise cutoff point for their intrinsic brightness. However, astronomers still need to determine which of these and other novel techniques are more accurate. So, as the Hubble tension intensifies, it opens the door to many possibilities that could lead to a profound understanding of the cosmos. Recently, the James Webb Space Telescope discovered the farthest black hole sitting at the edge of time. If you missed this episode, be sure to catch up on the exciting discovery.